Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. In the last video we introduced this idea of vectors in the two-dimensional plane, and we saw that we could think of them as directed line segments. That was, we could think of these arrows in our two-dimensional plane as vectors, but equally we could describe vectors in their coordinate representation form, that was in terms of points in R2. And in this video what I want to do is I want to look at structures that we can put on this space of vectors. So in other words, can we add these vectors, can we multiply them in some suitable sense, and can we subtract them? And let's look at some properties of addition and what we call scalar multiplication and subtraction. So let's go to our tablet. And I've already written the title in this time. So our title is something like vector addition / scalar multiplication in R2, and that's what we're going to study here. So we want to start off with a suitable notion of vector addition, and that gives us our first definition. What do we mean by the addition of two vectors? So if we let v, and we'll represent it here with an underline because we're saying it's a vector. In the notes it's again written as a boldface letter, but we don't use boldface when handwriting. It's difficult to do. So we let v equal v1, v2, and we use these square brackets to represent that it's a vector. And we let u equal u1, comma u2. Then the vector addition, so I'll put this in a different color, the vector addition of v and u is given by, as you might expect, we write it as v plus u is equal to, and we just add up the individual components of the vector. That is, we take v1 plus u1, comma v2 plus u2. Now it's important to note here that if we study this definition in a bit more detail, this plus here that we've written is different to this plus here. Right? This plus here is the usual addition that we use on the real numbers. In other words, given some real number here and some real number here, we add them together in the usual way, and that results in another real number. Similarly, this plus here is the addition between two real numbers. This plus, however, right, is an addition between two vectors. That is, I take one vector and another vector in R2, and I add them together and produce a new vector. So this plus is actually very different to this plus here, even though the notation is identical. So this might be an abuse of notation, but it's very common within linear algebra to use this, and it normally makes sense from the context. So it's fairly obvious here from the notation that this plus is the plus that we're discussing about between two vectors, whilst this plus here is about discussing between two scalars or two real numbers. We'll talk about what we mean by a scalar in just a moment. So how do we interpret this thing now in this geometric picture? How can we think about the addition of two vectors where we think of vectors as directed line segments? And this ties already to some of the stuff we've talked about in the complex number part. So if I draw my Cartesian plane now, this is R2. Make a note of that, that's R2. And let's say we take 2 points in this space. First, we take A and B. We can describe the vector in between them. And we can take some other vectors, C and D. Sorry, some other points, C and D. And let's say we take the vector in between them. Okay, so what does it mean now to add the green arrow to the purplish colored arrow? Okay, well the first thing that we want to do is we want to realize we're going to exploit this idea about what it means to say two vectors are equal. And recall that we can shift these vectors around freely around our space. So we can make them so that their length is still the same and their orientation is still the same, but they start and end up at different points. So let's write this green arrow. Let's start it now so we can write it, it's going to be equal to some other arrow or some other vector that emanates from the origin. So that's the same as this one here. So we'll rub this one out now. We've just effectively shifted it along. So now its base lies at the origin and its tip lies somewhere else, such that the length was the same as the other one and the orientation was the same. And we can do the same for the kind of purplish vector. We can write that somewhere like so. And we can rub that one out now. So these two vectors we can describe now as, give them some names. So we'll give this one the name u, and we'll give this one the name v. Now what does it mean to take u plus v, or v plus u? We'll realize that they're the same in just a minute when we prove it, but let's see if we can do u plus v. So in other words, what we're going to do is we're going to transport this vector here along so that its base now lies at the tip of this vector u, which is exactly like how we thought about addition in the complex plane. So in other words, we can think of this vector now, we can transport it along, and we can do it something like so. Okay, so this is still v. And now in this picture, we can think of this vector that goes along here, the one starting at the origin and going along so its tip ends up here. Hopefully you can see. This vector here is u plus v. And geometrically how we think of that is we first move along u, like so, and then we move along v, and that's the same as moving along this vector here. So u plus v in this picture is exactly just this vector here. So this is how we can visualize the addition of vectors on the two-dimensional plane from this definition up here. And you can see that in fact these two things are equivalent. So adding up the component-wise is equal to constructing this picture where you transport the vector so its base now, or you parallel transport it along so its base now lies on the tip of the other vector, and then you just move along that new vector. Okay, but let's look at some properties of u and v. Well, we can realize immediately from this picture we could have equally actually taken the green vector and transported the green vector, this one here, down so its base lies at the tip of v, and then we would have had the green vector is like so, and this one would be exactly the same. In other words, we've got u plus v is the same as v plus u. And we might want to see if we can prove that in general, right? Is addition on R2 defined in this way commutative? In other words, is u plus v the same as v plus u? Indeed it is, but that requires a proof. So we need to write our first theorem. So that kind of geometric picture motivates our starting theorem. So maybe let's write theorem here. And we'll shift that along. Okay. So our theorem says if we let u be represented in this coordinate representation as u1, u2, and v equal v1, v2, so these are 2 points in R2, or 2 vectors in R2, then it follows that u plus v, where this is the addition of vectors, is the same as v plus u. Now the proof of this is fairly simple, and it just uses the fact that the addition on the real numbers is commutative. Right? So we know that if we add two real numbers up, the order in which we add them doesn't matter. So expanding u plus v gives what? We've got u plus v by definition is u1 plus v1, comma u2 plus v2. But by the definition of addition on the real numbers, so recall that this is a different addition, that's the same as v1 plus u1, comma v2 plus u2. And that's because addition is commutative on the real numbers. So maybe I'll make a note of that on the side. Plus is commutative on R, on the real numbers. And hence we can just expand this back out again. In other words, this is the same as v plus u, where this is now the addition between two vectors. So that's our proof done. And we can make our box to say that we're finished. Okay, so that's a fairly easy proof. And another useful proof that is one that's worth checking is to see how the zero vector that we defined in the previous lecture acts on these vectors via addition. And it has this special property that, as you might expect, the 0 vector is the vector that when I add it to those vectors, it doesn't change them. So that gives us our next theorem. Which says for every vector, hold on, let's try again. For every vector in R2 we're specifically looking at here, it follows that v plus the 0 vector equals v. In other words, the 0 vector doesn't change our vector when it acts via addition. So in other words, it acts in the same way as how 0 acts on the real numbers via addition. But again, it's important to realize this is a different notion of addition now. This is the addition between vectors, and the 0 vector is a different notion of 0. It's not the same as 0 that you have for the real numbers. The 0 vector is multiple copies of 0. In this case, it's 0, 0 with this square brackets notation in R2. So if we prove this, again, the proof is rather simple. So let v, and we use the notation for a vector, we underline it, be v1, v2. So it's just a general vector. We haven't got any assumptions on it here. Then it follows that v plus 0, or the 0 vector, is v1 plus 0, comma v2 plus 0. And we know how this 0 acts via addition on the real numbers. Either it doesn't change that real number and it doesn't change this real number. In other words, it's equal to v1 comma v2, which is the same as v. So in other words, our statement is proven. And because of the fact that this thing is commutative, we've just proven that v plus u is always the same as u plus v. If we have v plus 0, that's the same as 0 plus v, which is equal to v by the previous statement. Okay, so the next thing to look at is to talk about a notion of multiplication on the vectors in R2. But it turns out actually we can't write down a sensible notion of multiplication of two vectors in R2. That is, we can't multiply two vectors and result in a new vector. But what we can do is we can multiply vectors by real numbers, or what we call scalars. And this is known as scalar multiplication. And geometrically how we interpret this is we just interpret it as stretching the vector by some scale factor. So let's write down our definition first. So, and I'll shift that down a little bit so we can see that better. So our definition goes something like the following. If we let v equal v1 comma v2, so it's just some vector, some coordinate representation of a vector, then the scalar multiplication of c, which we'll take to be as a real number. In fact, we can generalize this later when we do some abstract stuff to realize this can be an element of a field, but for now we're just going to do it for the real numbers. And v is defined as the following. We can write c times v is equal to c v1 comma c v2. And we write, let's maybe move that over here, the number c is referred to as a scalar. So that's why we refer to things as scalar multiplication, because we multiply them by these numbers here, c, in other words, real numbers, which we call scalars. And again, it's important to know that the multiplication here of c and this vector is not the same as this multiplication here. This multiplication here is the multiplication of two real numbers, because c is a real number and v1 is a real number, and likewise here we've got c is a real number and v2 is a real number. So this is the standard multiplication you know from primary school. But that's not the same as the multiplication that you've got here, right? Because this thing is a real number times by a vector. So it's again important to note that these are two different notions of multiplication, and that's going to be incredibly important when we start thinking about how to generalize this stuff. And just as a kind of quick geometric picture to draw again, how do we interpret this? I already kind of said that we can think of scalar multiplication as simply stretching some vector by that scale factor. So if I take some vector, let's draw it like this. I've got some vector here. Let's say this is v. Then if I do c times v, that's effectively just stretching this vector by some scale factor c. In this situation, I'm assuming that c is greater than 1, clearly. But if c was less than 1, that would either flip it by 180 degrees or would scale it down by some factor. But in other words, we see here that scalar multiplication is just the same as effectively scaling our vectors by some scalar factor, some real number. Exactly like we've seen as kind of on the complex plane. Okay. And let's just look at some examples now before we move on. So some simple examples. So if we take, like we've got in the notes here, we're going to let v equal minus 2, 4. Then I've just written a couple of scalar multiples here. Then we can take 2 times v. Well, that's going to be the same as taking, we've got 2 times minus 2, 2 times 4, which is the same as minus 4, 8. We could take something like a half times v, because that's just a real number. That's scaling it down by a factor of a half. That's going to give us 1/2 times minus 2, 1/2 times 4, which is minus 1, 2. And the last one, I've multiplied it by a negative number. So we see that this is minus 2 times minus 2, minus 2 times 4, which is going to give us 4 minus 8. Make sure we use square brackets here to denote that it's a vector. So that's how scalar multiplication acts, and we can realize it in this coordinate representation. It's rather simple. We just expand or just take our scalar multiple inside our individual components of our vector and just multiply each piece in the usual way that we would multiply real numbers. Now, if we've discussed vector addition, it would be reasonable to construct a definition of vector subtraction in R2. So that leads us to our next definition, and we can construct vector subtraction by just from vector addition and scalar multiplication. And we see that in the following way. So if we define, again, we're now taking two vectors because we want to subtract them. So let u equal u1, u2, and v equal v1, v2. Then the vector subtraction of u and v is given by what? It's going to be given by u minus v, we would write it as, which we can write as u plus minus 1 times v, in other words, minus v. So that's how we define it. And we can write that then as u1 minus v1, u2 minus v2. In other words, what we've got here again, this subtraction is not the same as this subtraction. We define subtraction as we take the first vector u and we add on minus 1, the scalar multiple of minus 1 and v. So we take minus 1 and v, which is minus v, and then adding those together gives this respective thing, because we know that we can define minus 1 times by a negative times by a real number just gives us minus that real number. So that's how we define vector subtraction. And we can also think of this noticing as well that multiplying our vector by minus 1 is the same as like how we thought of it geometrically for complex numbers, is the same as rotating that vector by pi radians about the origin. So let's go to our final example then. of how we would subtract some vectors. So again, this is rather simple. So we take let u equal, in the notes we've got 1, 2. And v here we're going to take to be minus 3, 1. Then what is the subtraction of u and v? We have u minus v is going to be, we take the first component of u and take away the first component of v. That's 1 minus minus 3. And then we've got the second component of u, which is 2, minus the second component of v, which is 1. In other words, we get 1 minus minus 3, which is 1 plus 3, which is 4, and 2 minus 1, which is 1. So we get 4, 1. So that's where we're going to conclude the video. And in the next video, what we're going to talk about is we're going to talk about extending this idea, this definition of vectors in the two-dimensional plane, to vectors in Rn. So that is, we're now not going to think of it in this geometric setting. We're going to extend it because it's reasonable, right, to define the Cartesian product of n many copies of R, and using that now we can have the coordinates of a vector in some n-dimensional space in Rn. So we're now going to kind of extend all this idea of kind of moving our geometric picture of vectors into this coordinate representation, and then using this coordinate representation we can extend it even further to some kind of more general notion of vectors in Rn, as opposed to just these ones that we can think of as arrows. So as always, I recommend that you read the notes after watching this video and to attempt any problems in the module handbook pertaining to the material discussed in this. So thanks very much for watching, and see you in the next video.